Okay, so I just wanted to go over the Unit 2 energy review questions. So we did the first one in class. Right, we have 4 objects. They're at 3 different temperatures. The cup is at 44 Celsius. The body temp is 37 degrees Celsius, body. And the air is at 22 degrees Celsius. Okay, so heat always flows from high to low, right? We need to know this for tomorrow's test. So it has to be in this direction, from the cup to the body to the air, right? So looking at the answer choices, right, bodies really means the hand. The only one that makes sense is D, right, from the cup to the hand, from high to low. The other ones are all, right, from the air to the cup. They're all going the opposite directions, from low to high. Same idea for number 2 here. We have 20 degrees Celsius, right, so high to low. Well, the only lower temperature than 20 is choice A, 15 degrees Celsius. Okay. For the 3 forms of energy, this was how we started the unit, the first few slides, right? Unfortunately, this is kind of like you need to know them. So first off, temperature. Temperature is measure of average kinetic energy. Temperature is not a form of energy, so it's definitely not C or D. We talked about how heat is thermal energy. Chemical energy is the energy stored in bonds, and electromagnetic energy is like radio waves or microwaves, right? It's waves of energy. These two are energy, but this other word, electronegativity, we're going to learn this later on in the year. This is not a form of energy. Same thing here, thermal energy is heat. The only one that we've learned so far is exothermic, but remember, exothermic is not a form of energy, it is describing energy. That energy is released. For number 5, we have 2 samples of water. They have the same mass, but sample 1 is at 10 degrees Celsius, sample 2 is at 20 degrees Celsius. So compared to sample 1, sample 2 contains lower average kinetic energy. Well, sample 2 is at 20 degrees Celsius, so it's definitely not. It's at a higher kinetic energy. Since sample 2 is at a higher temp, that particles are moving around faster, so it's not B. 20 has more heat energy because it's the same amount of mass as sample 1, but at a higher temperature, so more heat. Remember, highest average kinetic energy, we could just replace that word with temperature. So don't get confused by the mass. Which one's at the highest temperature? That is our choice A. 7, once again, average kinetic energy is temperature. Definition question. Same thing again, it's just the highest temp. Don't worry about the milliliters. The highest temp is choice A. Okay, once again, this is really like the same question. We're just wording it differently. Highest average kinetic energy equals highest temp. Don't worry about the phase, right? So highest temperature is going to be 30 degrees Celsius. All right, now there's a little bit of math in question 10. So we have 120 Kelvin. We want it in degrees Celsius. So look at table T. Our equation is K equals degrees Celsius plus 273. Okay, so I know 120 K equals degrees Celsius plus 273. In order to clear out the right side, right, we have to subtract 273 on both sides. And you will get that 10 is A, negative 153. Same thing here. Now it's 20K equals degrees Celsius plus 273. Subtract 273 on both sides. And we get that the answer is A as well when we subtract that. All right, exothermic. Remember, exothermic is exiting. Our heat is exiting, so we are cooling down. We're going from high energy gas down to liquid, down to solid. Okay, so we need choices in this direction. Boiling is liquid to gas. Melting is solid to liquid. Condensation is gas to liquid, that looks great. Sublimation is solid to gas. So our answer is definitely C. Same thing, release of heat is exothermic. So I need gas to liquid to solid. Right, my only option that makes sense is liquid to solid. Right, we're cooling down. The other ones are all endothermic. Same question, just different wording. Exothermic, it's going to be liquid to solid. Because again, energy is released. We're going from liquid that has some movement and we're cooling down to a solid. 15, we have our heat equations coming up. Okay, so we know the mass. We know that it's water, so we're going to circle water. Because what do we know about water? The specific heat is 4.18. It's at 23 Celsius. This is my initial temp. Absorbs 209 joules of heat. That is my Q. What's the TF? Okay, so since we have a delta T, they're looking for final temperature. I'm definitely going to use this equation. Remember, guys, that delta T is T final minus T initial. All right, so I'm going to really substitute that in. I'm going to say Q equals MC TF minus TI. All right, so plug it in. 209 joules equals 10 grams times 4.18, because it's water, times TF minus 23. All right, so you could plug it all in, divide by 10 times 4.18. Just to show you one other way, I feel like I didn't show you a more stepwise approach is, right, we're trying to clear out the right side and just get TF on the right side. So I'm going to multiply these two numbers. So I get that 209 equals 41.8 times TF minus 23. Okay. I'm going to divide by 41.8 on both sides. Again, I'm trying to clear out and just get TF by itself. So now I can cancel this. Divide 209 by 41.8. You get that 5 equals TF minus 23. Final step, add 23 to both sides. You get 28 degrees Celsius. All right, 416. What's the amount of heat? Okay, we're dealing with our 3 heat equations. Required to melt. Okay, this is your alert symbol. Melting is a phase change, so we cannot use Q equals MCAT because we do not have a change in temperature. Right? Think about our heating and cooling curve. The flat parts are the phase changes. We have no delta T. Because I am melting, right, I need to decide, am I using Q equals MHF or Q equals MHV? Since I'm melting, there's no gas, there's no vapor, right? I'm going to use Q equals MHF. They tell us, since it's not water, right? If it was water, we know heat of fusion on table B, but we have magnesium oxide. So they told us the heat of fusion is 1.9 times 10 to the 3. So I'm going to plug that in. I'm looking for heat, Q. I have 43 grams. And the heat of fusion is 1.9 times 10 to the 3 joules per gram. You just plug that all in, and you should get choice C, 416. All right, numerical setup to calculate the heat energy required to melt 100 grams of water at 0 Celsius. All right, this is nice because we don't have to actually plug it in. They give us the setup choices. If I am melting, again, phase change, I have no change in the temperature, so I cannot use Q equals MC delta T. It's going to be melting, so Q equals MHF. If this said to completely boil, then we have a vapor, then it's Q equals MHV. All right, so Q equals, we have 100 grams, they told us the mass, and it's water, so we have to look at the reference tables. Right, we have to see that the heat of fusion is 334 joules per gram. Table B. Okay, for 18, remember, gas is high energy. The particles are moving around really fast. They're going crazy, very high energy. gas goes down to a liquid, down to a solid, right? Energy decreases this way. So my only option is liquid to solid. Liquid to solid. All the other ones, liquid, gas, solid, liquid, are all the opposite direction. 19, what is the melting point? All right, we have two different plateaus. Right, so we're going to start from a solid. That solid eventually turns to a liquid. Then we have a liquid heating up. Then the liquid changes to a gas, and then we have gas increasing in temperature. So we need to know that melting is the first plateau, right? The second one would be boiling. So we look for the melting point. It's a little bit underneath 60. All right, looking at the scale of this graph, the answer is going to be 55 Celsius. 20, more heat equation. Right, amount of heat tells us Q. Melt, once again, is heat of fusion. 200-gram sample is our mass. We know we have water, so that's your sign to look at table B. Physical constants of water. Since it's melting, once again, Q equals MHF. I'm looking for my heat. My mass is 200. My HF, right, so look at table B. Your HF is going to be 334. So your answer for 20 is going to be C. Okay. Exothermic, again, exit. We're cooling down. We're going from high energy to liquid to solid. All right, that's exothermic. So our only option that makes sense is gas to liquid, right, going this direction. Everything else is the other way, right, is endothermic, warming up. All right, amount of heat, so that tells me Q. We have 100 grams of water. That's my mass. I know I have water, so I know that my C value is 4.18. And I have my change in temperature. Remember, delta T is T final minus T initial. Increase from 30, that's my initial, to 45, that's my final. So to do delta T, I have to do 45 minus 30. My delta T equals 15 degrees Celsius. All right, and then I just plug that all in. So same equation, the heat equation, Q equals 100, 4.18, 15. When you plug this in, you should get that 22 is B. All right, I have mass, I have absorbs. So I know this is a positive amount for my Q. The temperature increases 25 Kelvin. I have my delta T. What's the specific heat capacity of the metal? Right, so now I'm looking for my C. So same equation. I plug everything in. Okay. So we need to get C by itself. Right now, C is being multiplied by these two numbers, so we need to divide them. Right, so I'm going to do 15.1 times 25. So this way it clears it out on the right side. What we do to one side, we have to do to the other. So 15.1 times 25. Once again, in your calculator, guys, I know it's a little bit tricky. You'll do like 48.75 divided by 15.1 times 25. When you put that time symbols, right, think of PEMDAS, it will do the operation in the parentheses first. Because there's really no operation here in that parenthesis, it'll multiply it first, and then 48.75 divided by that value. And so when you plug this all in, you should get that C equals 0.129. All right, we have a cooling curve. Potential energy decreases while average kinetic energy remains constant. Remember, average kinetic energy, I could replace that with just one word, and that is temperature. So where on this graph is temperature constant or not changing? Well, BC and DE. That's my choice. And then the PE is decreasing, right? Because if one is constant, the other one is decreasing if it's a cooling curve, and increasing if it's a heating curve like this. All right, once again, right, obviously this is a big concept here, endo and exothermic. So for 25, now we're endothermic. Energy is entering. We're going from low energy to high energy. So we're going from the lowest, which is solid, gaining energy for a liquid, gaining energy for a gas. So let's see, freezing is the other direction, not A. Condensation is gas to liquid, not C. Once again, not D. Melting is solid to liquid, evaporation is liquid to gas. We're moving from solid to gas. We are warming up. That's endothermic. Okay, another KE and PE question. We have our heating and cooling curve. Right? We are boiling. So boiling is this plateau up here. What's happening to potential energy? Well, our average kinetic energy, our temperature is constant. So if KE is constant, PE must be increasing. So for 26, it's going to be C. All right, now our part twos. So we have carbon dioxide, dry ice, right? We did this lab in class. And we said at 1 atmosphere, 190 Kelvin. So this is temperature. They're at the same temperature. When we see this word compare, right? Compare means tell me about the two. Are they the same? Or is one higher than the other? Right? Or is one lower than the other? So compare amount of thermal energy in a 1 kilogram block of dry ice to the amount of thermal energy in a 2 kilogram block of dry ice. Right? So we have the 1 kilogram, we have 2 kilogram. They're at the same temperature, 190 Kelvin. They're made of the same thing. So if I have two objects made of the same material at the same temperature, whichever one has more mass has more energy. All right, so we can say the 2 kilogram block has more thermal energy. And now I've answered the question. I have compared them. You could have also said the 1 kilogram block has less thermal energy. So once again, compare the potential energies of the water molecules before and after the water condenses. So remember, condensation is going from a gas to a liquid. So we said that energy, right, what has the highest energy is a gas. And then it goes down just liquid, then to solid. So the gas has more potential energy. So we could say in a few ways. We could say the water vapor has higher potential energy. Or we could also say that before condensation, it has higher potential energy. All right, heat flow, dry ice and water vapor. It tells us that the dry ice is at 194.5 K. The air is at 298. Right, so it's going to go from the air, or the water vapor, to dry ice. From high to low. So once again, this is really the same type of question. Gas has more energy, right? So we could just say that the water vapor has higher potential energy. Once again, a heat flow question. Well, when we bake muffins in the oven, right? The oven is hot, 200 degrees Celsius, and our muffin batter is at room temperature, right? So the oven heats up our muffins. So heat is going to flow from the oven to the muffin for that one. Okay, convert the melting point of mercury to degrees Celsius. Now, when you read this question, like I know when I read this question, I said, well, I don't know the melting point of mercury. I can't memorize everything. That's why we have table S. So I looked it up. I went to my table S. I found mercury, and the melting point is 234 Kelvin. And I need that in degrees Celsius. So I'm going to use table T. I'm going to use my equation. Take the time to double check you have it right. It's 234 Kelvin equals degrees Celsius plus 273. So I can subtract 273 on both sides, and I get that that degrees Celsius equals negative 39. All right, that is my final answer. Okay, from minute 4 to 9. I'm running out of time here, so I'm going to go a little faster. Really important to read. We have a liquid sample. All right, liquid at 194 Kelvin. So this is actually a liquid cooling down, then liquid to solid, then a solid. So during time 4 to 9, freezing happens. Liquid to solid. All right, once again, compare the kinetic energy. Well, okay, remember that average kinetic energy equals the temperature. So where does it have more temperature, at 7 a.m. or at 3 p.m.? At 3 p.m. I think we could say bottle has more average kinetic energy at 3 p.m. Okay, so the bottle, the water heated up. It went from 12.5 to 20.5, so it must have absorbed energy. So energy transferred from surroundings to water. Okay, thermal energy, numerical setup. Well, a few things. We know our delta T. Right, the bottle went from 12.5 to 20.5. So final minus initial is 20.5 minus 12.5. You get that delta T equals 8. We know our mass is 800 grams. We know that our C, because it's water, I know my C is 4.18. So I could plug it all in. Q equals 800 times 4.18 times 8. And that's my numerical setup. All right, heating curve. DE has higher kinetic energy, right? DE is at a higher temp. And finally, during interval AB, right, this is AB. Notice how we have two plateaus. So this has to be solid, that's liquid, that's gas. So during AB, it's a solid. So we're just going to draw a solid, right? So you're just going to draw at least 6 molecules. 1, 2, 3, 4, 5, 6. All right, and then you're done. All right, so hopefully that helped, and good luck on the test tomorrow. You got this.